Hello, we are back to uh, extend what we have studied from the last clip, okay, about one-dimensional heat equation. Today we're gonna, in this clip, we extend the analysis that we use to apply for the two-dimensional heat equation in this following form. Okay, let me recall you the original idea of one-dimensional heat equation, which was in this form. Okay, that the rate of change of heat, okay, over time, okay, equal to some positive constant value of the acceleration of heat over the dimension of the object that the heat has been transferred to. Okay, so in the one-dimensional case, the object is only consider only one dimension, the dimension of the object, which is corresponding to the x-axis, okay, which is axis between 0 to L. Okay, but now we are back to consider in the case of two dimension here. Okay, so we just expand to in the acceleration order term in second order term, okay, of heat flow, okay, over axis x and axis y as the acceleration, which is the you can see there is in the second order term. Okay, so you can now guess that in the third order term you just add one more term, that plus curl square of u over curl t square. Okay, and therefore now your domain have been expanded. Instead that you only have u of xt, now you decide that what is the heat flow over the coordinate of x and y at time t. Okay, and your initial condition now become at time t is equal to 0 for any xy, okay, that has a upper bound and lower bound. X is between 0 to L sub x and y is between 0 to L sub y, and t is greater than or equal to 0. So u of xy t is equal to 0 with some specific f sub xy. Okay, and this is a boundary condition. As we extend the boundary condition that we study from the in the case of one dimension, in the two dimension case, we consider both Dirichlet boundary condition, which is the zero order form, and in the first order boundary condition it belongs to Newman boundary condition. Okay, so this is just extension by adding one more dimension to the problem. Okay, therefore in the Dirichlet boundary condition, okay, you consider when x is equal to 0 for all y at time t, and also have to be equal to u at when reaching the upper bound of x at L of x, and for all y at time t is equal to 0. The same for the upper and lower limit of y, okay, in the u of x at y is equal to 0 at time t is equal to u of x, okay, at L sub y at time t is all equal to 0. And when you extend this condition, evaluated, okay, after the first derivative, it becomes Newman boundary condition. And you might remember that the reason that we have these two conditions is that it's going to alternate the cos and sine term. Okay, if you might remember, that leading to the general solution in the series form that we call the Fourier series. That's what in the first dimension. If you might this one, I might recall you that the general solution, okay, in each case, okay, is in one dimensional case, it belong to yeah, it's quite long. Okay, we're gonna turn back a little bit. Okay, here, okay, this is no, just only one dimension of x. Okay, yeah, and this one is Newman condition. Okay, so you have a cos, and then if under this condition it's going to be b sine. Okay, and when you analyze it, okay, this is how you end up. Okay, you can find a general solution for b sub k, okay, and a sub k over here, okay. Okay, and this one belong to the as you might remember, the Newman condition, but for Newman condition you need to find a sub k, okay, and then for Dirichlet condition, okay, you end up having to find b sub k, okay. I think it's reverse. Dirichlet condition is you need to find a sub k, right? Oh man, we have to go back and look at it. Okay, this is for Dirichlet condition is here. Okay, it's in the B sign. Okay, and when the Newman condition was used, okay, the solution is in the A sign. Okay, and both of these coefficients are in the series. Okay, can be estimated. Okay, under the condition that if a function in the initial condition at time 0, okay, the function of x or function in this case we replace x by t, okay, when is have some property of what we call the periodic function here, okay, they have a periodic function over here. So we're gonna extend, and this one for b also, okay, we're going to extend the whole idea that we studied from last clip after we adding one more domain we call y here, and consider in both Dirichlet and Newman boundary condition. Okay, again we're going to start by using this separable function technique in the term of multiplication form. We believe that u of x and y in time t here is in the product form of some independent function of x times independent function of y. We call capital X of x, x in terms of x, and capital Y in terms of y, and then capital T in terms of small t here, okay. Therefore, when we replace u of x, y, t to this original two-dimensional heat equation, okay, this is just a result because on the left hand side is a first order over t, okay, and you know that x this function of x and y become a constant value, but just find the derivative here of t. This is the first order of t, and also this one is alpha square is a unit conversion, a positive unit conversion, okay. And you get here, okay, this is the second order of u of x, y, t over x, and second order of y, okay. Therefore, it's only reflect to the order that of the function that belong to x and belong to y here, okay. And then if you divide it on both sides by alpha square y of y t here, okay, you can see that on the left hand side, okay, y of y decline to each other, okay, so the remaining is x by x t times t first order of t capital T, okay, over t divided by alpha square times capital T in terms of small t, okay. On the left hand side, okay, the first term, since you divided by alpha square y t, the first term, the only remaining term is a second order of capital X in terms of x, okay, in the second order form, okay. And the second term over here, okay, you know that you end up just only t inter t can be cancelled to each other, okay. But the left hand side you still have x of x and capital second order of y on y, okay, divided by capital Y in terms of function of y. Okay, so we rearrange the term by moving to the same one side, okay, moving all the function into one side, okay. In this one we remove this to this, okay, so that make the other side equal to 0, okay. So this term still remain here, okay. But this term, okay, this is a second order term. But this term is that the common term is that x capital X is a function of small x. This one they also have capital X as a function, okay. in terms of small x. So we take this out of the bracket, okay, with a common multiplication function, okay. So the remaining term in here, the first term here with the positive side, you have a second order of y and then divided by function of y, okay. And then this one when moved in the same side, it become minus sign of this one, t, okay, first order of t divided by alpha square of t, okay, and they have to be equal to 0. Okay, so this is in the form of we try to rearrange the term. Okay, this is in the second order form. Okay, and then what we are doing next? Okay, over here is that, okay, we divided on both sides also. Okay, over here, remember the original equation here we divide both sides by it. Now we use alpha square and we use the second uh, x of x, okay, times t sub t, okay, divided on both sides, replacing y of y by x of x instead of. You end up, okay, by rearrange the term here, okay, using a similar fashion. We trying to, in this case, okay, once you divided by x alpha square and then x of x times t sub t, okay, this term will have a coefficient of 1 just like this, okay. And the remaining term, okay, in the similar fashion and rearrange the term, you get another form of solution like this. And then the final one, we divide both sides by x of x times y of y, okay, on both sides, so that the remaining term, the term of t by t here on the left hand side, you can see that it have a coefficient of 1. And then you move the common term of t by t on the right hand side to the left hand side and rearrange the term here. So end up you are now having a 3 ordinary differential equation. You might say that it's an ordinary differential equation because there's no more partial differential equation anymore. It's become ordinary differential equation. But in the form that they look have a 3 equation, and you have 3 functions you need to find, which is capital X of x and capital Y of y and capital T of t. Okay, so how are we gonna do it? Okay, to simplify the problem, we're gonna let this, suppose capital B is this function, capital C is this function, okay. And then if you consider alpha square times B plus C, you're gonna end up at this, okay. uh, why you have b plus c like this? Because you can see that when alpha square, when you use b by c by this substitution, the alpha square will cancel, okay, the division of the first term in over here, okay. So when they over here, okay, let's say is okay. This one is simple because you use alpha square, you end up having this in additive, and this is a minus sign. But the first term here, okay, the first term, I believe that the first term have some, once you have alpha square times b plus c, okay, you end up, you don't need any of this. Alpha square over here is become 1. So change this, okay, alpha square here is only 1. So the left hand side can be only 2 times t by t divided by tt. Okay? Okay. Yeah, have to be like this. Okay? 2 times t first order of t divided by t as a function of t. Okay, because when these two plus together, okay, the division is the same, but since you use alpha square multiply b plus c, alpha square should be cancelled here. So there's no alpha square over here, okay, but alpha square in this multiplication form is correct. So this one is only 2 times t first order of t divided by t as a capital T as a function of t. Okay, therefore you end up having this. Okay, if I replace this t, first order of t minus alpha square b plus c, since alpha square b plus c is here, okay, you might take a look here there, because the alpha square is b plus c is 2 times t divide the first order t divided by tt. Okay, but you using this term, okay, but this one is you use alpha square b plus c times tt cancel each other, you end up having 2 times t first order of t, and when you have this term, put this term in and minus this, you end up getting the first term, you get minus t first order of t over capital T by the small t here. Okay, first of all, okay, this alpha square should be replaced by 1. Okay, so this one just divided by tt. Okay, and this t pi t, okay, minus alpha square b plus c tt over here. Okay, when you apply tt to this, tt just cancel the first term here, you end up having 2t first order of t over t. When you minus this value, okay, with t pi t, so the only remaining term is t by t. Okay, and then the remaining part here, okay, become the second term, and since it's minus, so minus and minus become plus sign. Okay, and this one t by t, and then if you move to the other side, okay, you move from left hand side become right hand side, and right hand side become left hand side, you end up having a third equation here. Okay, so this is just to simplify the form. Okay, simplify the form from the original one here. Okay, so this is the original equation here. You can simplify it and written down as here. Okay, with capital B and C is in this term, and with boundary condition here, you can see that with in this case, if you consider the Dirichlet boundary condition first, you end up, okay, if you replace u of xyt with this form and evaluate under the Dirichlet condition here, okay, you end up, okay, having this boundary value problem, okay, with x of 0 equal to x at Lx is the upper limit of the domain x, and lower Ly is upper limit of the domain y. Okay, and but you might take a look at that b and c here is also not a constant. Okay, it's another differential equation. Okay, it's another differential equation. We just write it just to simplify the form. Okay, so now by using similar analysis that in case of one dimensional heat equation, okay, you can see that why do I get here that oh sorry, okay, which is we want to find x of x, y of y, and t at t, okay, in terms of bc and alpha square over here, okay, with this boundary condition. As you see that this is a second order differential equation. By second order differential equation, you know that it have to be, you remember that we did in the part of over here. Okay, this is what we did here, you remember, but we used minus lambda in instead, lambda alpha square. You remember this is from the first equation, from the last clip of the separable function technique over here, and then you simplify, you end up having this corresponding differential equation which exists only complementary solution. And then the first equation is similar to each other. It just replace lambda by b, okay, and you are having a similar equation for y. And the third equation, you just replacing lambda here by this term, b plus c, okay, by b plus c over here. Okay, so if you can see that this is quite very similar to what we did in the first dimension. So we can apply over here that since xm of x, okay, it become cmx, okay, the constant value sine, and then mu of m times x, and y of y is in the similar form, and t of t is also in the similar form. Similar form to what? To what we did over here. You remember that in the first dimension, what we did here? X of x with the boundary condition, okay, we can end up, and you can see that x of x is here. Some constant, rely on the n value, okay, that satisfy the boundary condition, and then sine term, okay, sine. And then for t, okay, so therefore when x is in this form, y is also in a similar form, and t also in a similar form, but just the difference of the exponent because of the coefficient that multiply to this corresponding equation, differential equation, ordinary differential equation. Okay, so we borrow the results here. Okay, let's say that we borrow the result over here. Okay, except to use it here. Okay, to use it here. Therefore, in the similar way, okay, we end up having x at we're using a different notation now to meet with the, because now we need both m and n because you have two domain, both x and y. The x function and y function is a constant value sine of some specific parameter we call um sub x, and sub x have to be in this form, m pi divided by l. Okay, why? Because of the boundary condition. Because of the boundary condition. Because x of Lx have to be equal to 0 also. And x of Lx will become only 0 when mu m is in this form, m pi divided by Lx. When you replace this x here is the same as x here. I'm using a mistake here. X here is the same as x here. As x here. Okay? So if you replace x by L sub x, okay, this L sub x, and you substitute mu sub m by m pi divided by L sub x, okay, L sub x cancel each other. So you end up having sine m of pi. Sine m of pi is always equal to 0 for all m. Okay, and m can start from 1, 2, 3 up to infinity. Okay, and in this case, okay, when mu sub m is here, okay, you can see that why do I get up that b is minus mu m square, because if you look at this original here, okay, b is here, okay, therefore with this form, okay, you remember that it have to be sine of square root of mu sub m, uh, square root of mu sub m. Okay, and square since but this value have to be equal to uh, square root of b. Okay, square root of b, therefore the b themselves have to be square of this, and it reverse the sign also, it become a minus sign. Why? Because of the non-negative negative nature, okay, that we used previously on in this. Okay, you can see that in the early one we get minus lambda equal to here, therefore minus lambda, okay, if you square on both sides, minus lambda will become n square pi square divided by l square, therefore lambda is equal to minus n square pi square divided by l square. That's what we did here, and then we apply the similar situation here. Okay, over here, since this is a square root of b, okay, square root of minus b, let's just say square root of minus b, therefore b have to be equal to here. The same for the y, this have to be the square root of minus c, therefore c have to be equal to here. When v mu m and v sub n is equal to this one, m pi divided by l sub x, and n times phi divided by L sub y, when m and n start from 1, 2, 3, 4, 5 up to infinity. Okay, and t sub t also, since this is the first order, okay, so it's easy that you end up, and the characteristic root is this one, alpha square b plus c. Okay, so you can see that since this one, okay, lambda mn here, okay, you can see this is alpha square b plus c. Okay, this is when you put b plus c by here, okay, by substituting here, because mu sub n and v sub n is in this form, therefore b is here and c is here. Okay, and the minus sign, just take it out, this is b, therefore alpha square b plus c is here. Okay, when you get this is a minus sign. Okay, therefore this one is the general form of tt is that kmn. Okay, so this one have to rely on both parameter m and n, but instead of xm and yn here, rely on two parameter of m and n. But for t, you have to rely on both m and n, because their exponent form rely on both b and c value. Okay, so you end up having this b plus c is equal to here with alpha square b plus, you have minus sign over here. So if you just take this as a lambda sub mn, okay, equal to the positive value here. Okay, so it's just going to be the minus lambda mn is equal to alpha square b plus c, which is the exponent over here. So just play around with the notation. Okay, so this one you end up having this general form over here, and then after this, okay, you end up over here that you get this general formula form that rely on both m parameter and n parameter of coordinate x, y times t as some constant value, and you have term of sine and term of sine, both of this because of the Dirichlet condition. Okay, and this is from boundary condition. Okay, you end up be able to find this parameter, and then this is the exponential phi in according to the t function over here. Okay, so this is and all the constant multiply to each other become b star mn sub mn. This is a type of x function, type of y function, times type of t function. You can see that b star mn is equal to all the constant for each model. Okay, this one from this one, and from this one multiply to each other, and since it's a constant, become the new constant value, and m and n start to here. Okay, and what we call is that this is a u that rely on mn. What about u x y t for all mn? And certainly the superposition principle for any specific m and n contribute to u of x, y, t. So for all mn, it becomes summation m for all m and summation start for all n of this b star mn. Certainly become the general form. Okay, and mu sub m and v sub n is here. Okay, mu sub n is m times pi divided by L sub x, and v sub n is equal to n times pi divided by L sub y. Okay, so this is in the general form of u, x, y, t. Okay, so in the next part is that how do we find b star mn here, b star sub mn. Okay, you might try to follow, is just using the same analysis that we did, what we did for the one-dimensional case, except that we add, when you add more dimension to the problem, it just keep extending the parameter, okay, combination in the model. Okay, so given the boundary condition for this condition, okay, u of x at coordinate x of y at time is equal to 0, equal to, okay, to f of x, y again. Okay, and this one, okay, this sign, I forgot to write down this one, mu sub m, okay, and v sub n over here. Okay, this should be sine of v mu sub m times x times sine of v sub n times y, just like what appear the function appear in over here. But you know that when t is equal to 0, this term is equal to 1. E to the 0 is equal to 1. So this also become the question that what is the B star of Mn? Okay, what is the B star of Mn? Okay, and this one is in the form what we call the double Fourier series. You remember that in the one dimension you end up having a one dimension just a single stage Fourier series. But when you extend the heat equation to two dimension, you end up having a double Fourier series. So really similar analysis. So what we did in the first order term, you have B abandonment. Okay, you need to this one is for Newman condition. Okay, first, okay, this one is keep the problem remaining, and they will solve it toward the end. That what is the relationship? How, if you know f of x y, okay, how define B star sub Mn? Okay, and for Newman condition in a similar way, this is the condition that boundary condition that rely on the first order term. Okay, therefore, okay, we show a little bit that this one, okay, this is the first order, second order differential equation for complementary solution. You end up having here, which is this one. You using this form because it's a non-trivial solution. Okay, but you need to find the first order term. Okay, because the boundary condition is in the first order. So you find differentiation over here. Okay, I'm not gonna go to this. It's just show directly how you end up. This one you find derivative of cos, you get minus sign, then you need to find derivative inside the angle of cos also, that you end up square root minus b of times x, and you find derivative over x, you get a constant of square root minus b multiplied over here. So this one is the first order term. And when you put the boundary condition here for the for both sides, okay, at the lower limit at 0, okay, when you get 0, the sine term is becomes 0. So the only cos term remaining, and the cos term when 0, the cos term become 1. So the only way the low the first derivative at evaluate at x equal to 0 can be 0 is that this constant of c sub 2 need to be equal to 0. And again, you this is how it come out that you remember that you get sine when you're using sine term when you're using the Dirichlet condition. So when you use Newman boundary condition, it becomes cos term because it's all reversed because of the first order. The reverse between sine and cos when you find the first derivative. Okay, so it in a similar form. Okay, when you use Newman condition, you end up having a constant time cos term and constant time cos term and in y term also. And also with the boundary condition at L sub x, okay, you end up having square root minus b is must be equal to m times pi divided by L, because square root of minus b will be using to multiply x, okay, become the cos angle over here. Okay, and the only way that at boundary at the upper limit will become 0 is that minus b need to be equal to in this form when m start from 1 to infinity. Okay, so in the so it end up, okay, sorry, end up in a similar way that what we did here. Okay, what we did over here. Okay, except that it changed sign to cos term. Okay, cos term, and with mu sub m and v sub n in the same fashion. We just change the domain x to domain y, and that lead to the results of b, capital B and capital C need to be equal to minus mu sub m square and minus v sub n square. Okay, that's y minus still hold because this is square root minus, so when you square it, it become minus b. Okay, and then you can see that this one is obvious to show you here, become minus b equal to m square pi square lx square. Therefore b need to be minus mu sub m square. Okay, when mu sub m here, and the same as v sub n over here. And then now you can see the trend. Okay, t sub t T a function of capital T based on the small t is also a constant value times e to the minus lambda square m n t, and you might recall lambda square m n is the same as lambda m n that you find over here. Okay, because t at t is nothing changed because it's a e exponent function. If it's an exponent function, as you might remember, if you just find the derivative, it's gonna repeat themselves. It's not alternate from sine to cos or cos to sine, just like a sine cos function. Okay, so this is how it look like now, the tt. So therefore, the u function of m and n, okay, evaluated at x, y, and t over here, become another constant we call a star mn. It's a multiplication of for each constant in each separable function. Altogether, we combine it and call a star m sub mn, and this become cos, okay, cos term, and then the exponent function is for t function is the same. Okay, and this one also, that when this one I didn't forget to put mu sub m and v sub n here. This is mu, okay, this is u, okay, just not to be confused. This is mu, this is u function. Therefore, u function evaluated at xy t is equal to 0 is become f of xy, and certainly with superposition principle, this becomes the summation form, m equal to 1 to infinity and n is equal to 1 to infinity, and some constant value times cos term. Okay, and this is another part of double Fourier series, and the key question is a star mn. What is a star mn for a given f of xy? Okay, so if you combine between these two terms from the both Dirichlet condition and Newman condition, okay, you end up having these two terms added together. This is the first term is for in summation here is belong to Newman condition. The second term that multiplied by B star mn is a Dirichlet condition, and certainly you need to have a constant, okay, f of xy evaluated at some constant value. A in this case we used to call a sub 0, okay, this one become a 0 0, okay, double 0, and this one is in the form what we call the double Fourier series, okay. And the same way, if you following the footstep of one-dimensional Fourier series here, in this case I simplify to make it easy for you. We didn't in for the first dimension Fourier series, we replace x and y to become the no, there's no y, replace the x domain by t domain. That quite sometimes confusing with the another t that we used before. But in that case, I just want to try to link to the application that for any time domain, okay, you can use you can with the periodic signal nature, okay, which is repeat itself, okay. But in this one, we're not doing that. We're gonna do something like, if you integrate all for all the range of x and range of y, okay, on both sides, okay, and we're trying to after this, okay, f of x y on both sides, okay, you end up, you can see there, you find the integration of cos and sine, okay, cos and sine, okay. And if you might recall that I'm not going to go to this again, we have done that. We can combine the term expand the term of cos become if you might remember that this is what we did over here. We refer to the trigonometry function, cos and sine become sum of cos sum, okay, and subtraction of sine sum and sine minus, okay. So similar way we using this trigonometry principle, okay. You end up over here that okay, that this cos since it's an integration of cos and integration of sine, okay, you can see that when you integrate within the all for all domain, okay, and if that within that domain, if it's a periodic function, it repeats itself, it's cos and sine. So you can see that for cos function and sine function, the area under the curve cancel each other. Okay, if you apply it for the whole period, okay, you can see that the cos function start from 0 and then you go peak to 1 and reduce to 0 and then go down to -1 if you might remember, and then go up to 0 again. And when you find the area under the curve, they cancel each other because it's go to different direction. So it means that this term over here, if the function of x, y satisfy the periodic nature just like what in one dimension, but it have to be, this one is a little bit complicated because it's a two-dimension case, okay? But in one dimension you can say that okay, it's gonna repeat itself, but in two dimension it means that if it's gonna be both periodic in with corresponding to each domain, okay? So the characteristic equation of periodic or cycle of f of x y, okay, need to be extended from just like what we did in one dimension, so that these two terms you can claim that this term integration of cos, okay, integration of sine here is equal to 0. Okay, you can see that since you try to integrate the cos, okay, over here, okay, you end up, okay, integration of cos, what is the area under the curve of cos function? 0. This cos function 0, sine 0. So the only remaining term is this one. And within this form, okay, this side you have a sub 0 is constant and dy by dx. So this is a different is l sub x minus 0, l sub y minus 0, and multiply to each other. That become the multiplication. And you move to the other side, you get this 1 over l times x, l of x times l sub y, okay. And this integration form, when you know f, the type of function of x of f of x, y, b, you end up can find is 0, 0. Okay, and similar analysis for when you consider this term, okay. Okay, if you just multiply, okay, this one, okay, you can see that for this one, this if you want to find a star mn, okay, okay, you just multiply, okay, a sub 0, okay, 0 0 there by cos of mu sub k x and v sub l y, okay, okay, and this one small l is different from l sub x and l sub y, mu sub k and v sub l, okay, okay, and in this one, okay, certainly you know when a sub 0 is become this one, uh, when you use this, okay, and you find the integral for all range of x and y, okay, and if you multiply by cos of mu sub k times x and cos of v sub l times y on both sides, okay, the first term that belong to the a sub 0 0, you know that with cos over here, that independent function of x and y, you can separate this form, okay, this one cos, and you know that it's going to be equal to 0 because it's area under the curve, okay, equal to 0. But this one, okay, this one, okay, become cos and cos and sine cos. Certainly you can use a similar trigonometry analysis trying to over here, okay, cos mu, okay, this is a half of cos sum plus cos minus, okay, okay. Uh, in only one case is that when m is not equal to k, okay, and this evaluation where if m is not equal to k, is always 0. Why? Because when m is not equal to 0, this is not the cos 0. Okay, it's got to be cos of some function. If that going to be cos of some function, you know that from this one is that you integral based on cos function is always 0 over the period of 0 to l sub x, and this one. So except when m is equal to k, okay, the first term is 0, but the second term is become integral this one x divided by 2 dx, okay, over here. So okay, this one except for m is equal to k over here. Okay, so when m is equal to k here, mu m and mu k, you get this one. Suppose that v sub k is equal to u sub m. Okay, m is equal to k. It both u sub k times cos square of u sub kx, because both term is the same function. Okay, when you know cos square over here, you can use the property of uh, cos square theta equal to cos of 2 theta plus 1 divided by 2. Okay, trying to eliminate the cos function, since you know that integral of cos is always 0, okay, over the period. So the remaining term is only 1 by 2 over here, which is integral 0 to Lx of dx divided by 2. That the resulting of this evaluation, you get L sub x divided by 2. Okay, so which means that the first term over here, when m is not equal to k, m not equal to k, okay, you end up for this cos, okay, both of this, okay, the first term and the second term also, when n is not equal to k, when there's only one thing that you get all this is that when you get L sub x divided by 2 over here, and the second term over here you get L sub y divided by 2. Okay, since it's multiplied to each other, so the result, this is pretty similar for cos here. For y, it's always 0 when n not equal to L, but since it's equal to L, okay, it becomes similar to what we did with the x. You end up having L sub y divided by 2. And also, okay, cos and y, okay, but for sine cos and cosine over here, okay, if you using apply the similar analysis, try to change the multiplication form to a summation form, you end up can be evaluated that all of these terms have to be equal to 0 for all m, even though at m equal to k and n equal to L. Therefore, the only term that a star here is belong to at for some specific k and L. Okay, it's only L sub L sub x divided by 2 times L sub y divided by 2, and this 2 times 2 become 4, and then move on the side, on the other side, you end up being to find a star kl when k start from 1 to 3 to infinity. Okay, so this is when you know f of x y. Okay, so over here similar analysis. Okay, if you consider f of x y, instead of multiply by cos, you multiply by sine on both sides. With similar analysis, you end up can show with a similar logic that we did here for a sub kl. You can find that we move to b star kl over here. Okay, similar analysis, you end up having, you get b kl is 4 divided by l x divided by ly, and integral here of x over y, but instead of cos becomes sine. Okay, and I think that you can see the trend. So the homework, this is the first homework for the partial differential equation. That if you extend both distance and Newman boundary condition, therefore the u function become u of x, y, and c at time t, and this second order term, this one, I'm really sorry about this. You need to put square over here. Okay, this is all of these two terms need to be second order. Okay, need to be square here. Okay, I try to correct, and there's been so much mistake here that I and this is also the possible boundary value condition. Okay, for all LA, for when you add the x and y and c coordinate over here, you need to x at 0 for all y c t and u at the boundary of x is L sub x, and for y also start from 0 to L sub y, and you have one more at the c that you can c start from 0 and end up with the highest value no more than L sub c. Okay, and certainly this one next time in the next clip I try to correct this have to be 0. U of x y c at time 0, okay, need to be equal to f of x y c. Okay, so this is the if you extend this for the three-dimensional heat equation, okay, uh, you probably can guess. Okay, for example, this one, instead of KL, you need one more index over here, and this one should be 8. Okay, and you have L sub c. Okay, this one cos, there are three terms of cos. Okay, cos of the response to x, and cos of y, and cos of c. And thirdly, this one also sine of x and sine of y and sine of c. And this one should be a function of x, y, and c. Okay, remember that. Okay, this t, okay, have to be 0. Okay, and this one you need to add the square over here. It's become the second order differential equation of u function. Okay, so this is just for you to review your knowledge that you study from this clip, that for we from the last two clip, okay, that when we start for partial differential equation, we trying to derive a general form of the solution, and it turned out that it become a series, and it's well-known series called Fourier series. And within the Fourier series, you need to find the coefficients, okay, that multiply the sine and cos term in the series. And you can see that in one dimension, okay, you end up having a one-dimensional Fourier series, and when you extend to the two-dimensional heat equation, your solution is in the form of a double Fourier series. Okay, for three dimension, going to be a triple Fourier series form. Okay, and that wraps it up for the classical. This is where it all starts for partial differential equation and the Fourier series. Okay, the linkage and relationship between two of these uh, topics of one is in the differential equation, partial differential. The other one is in the in some of the general form that satisfy the solution of the equation, which in the series form we call the Fourier series. Okay, so in the next clip, okay, we will continue to look at some other extension of the well-known partial differential equation. We're going to call this Laplace equation. Okay, and I hope that you go back and try to review what we study. Okay, especially in the last two clips about partial differential equation. Okay, so that you get familiar when we continue with the what we another type of equation we call Laplace equation. Okay, until that time, okay, go back and review what we have studied. Okay, see you.